Today I will talk something about the distributed coding of Sparse signal. Yeah, we know the Sparse signal comparison is a kind of comparison method. This paper just want to demonstrate that if you want to use a certain bit to compress the signal using comparison, you cannot get a reliable compression given a certain bit. And I will explain it in detail later. And then they suppose use use a distributed source coding to compress the contact bits after the compressive sensing. And let's review something about the Sparse signal first. And suppose U is a vector with constant, and this vector is only have k non-zero entries. So this is a k-sparse vector, and we have a matrix V, and x equals V times U, and U is sparse, and x is a signal respect to the matrix name of the Sparse signal. And we define alpha equal to k over n is the sparsity ratio, and suppose we have a matrix Y and Y, and X. X in the subdomain is the sparse respect to V, and the X is the constant, and here phi is a matrix with constant and pi. Y is the vector fm, and this is a compressive representation of x here with respect to phi, and x in another domain is a sparse vector with respect to matrix V, and is a k-sparse, so x belongs to one of k n choose k subspace in R. Here, this is if you have
so I'm missing. Which one is sparse? U is sparse.
U is sparse.
Okay, U is sparse.
U is sparse. The sparsity is k, and the x equal to V times U, and y equal to phi.
Are m and n just arbitrary, or is m less than n?
M should be
Much less than.
less than n. And given U is a k-sparse, then we have and the mass of U is n. Then we can find the n choose k number of different combinations of U.
Can you repeat that last one? The U and M?
Suppose n equal to 3, okay, and k equal to 2. Then we have 3 nodes here, and mark that 1, 2, 3. Then u can be 0, 1, 0, 1, 3. Something like this. So the total in non-sparse items is k, and the total mass is 1. So we define entries k as the total number of entries. So the entries k and factor over 0. So given a u, it must be one of any u must be one of the subspace of entries k, and if m is larger than k minus 1, then we can recover u according to y. By using some exhaustive search in a matrix, and we suppose GA is equal to this number, this total number of entries. And
Excuse me. Suppose m is bigger than k plus 1.
yes,
All of them is just something suppose that. All of this part.
yeah, all of that is all that. If not, you cannot recover x to y.
K plus 1 is sufficient. Is that
Yeah, the minimum number is not. By using exhaustive search of
okay.
not
It's just sorry.
OMPL. This is exhaustive search. And so this is so if we use exhaustive search method, we need m should be large k plus 1. And there are many other compressive sensing, many other methods to solve this problem. And for example, we can use a linear programming method, and if we use a linear programming method to solve this problem, this is one. We need m is approximate to k times l. This is the threshold. This one is hard to solve this one if we use a linear programming to solve this problem. Given y, we want to know x. Suppose x is a domain is sparse. And if we think there's a noisy here, so we have we receive y hat equal to phi x plus a noisy beat. Then in this case, it's also a problem. So we use this equation, this item, make sure the signal is sparse, and this item make sure the estimation is similar with the true result. And after is parameter to evaluate the sparsity and the penalty. And in this case,
So right now we have 3 amp here.
if we use exhaustive search, we only need amp arch equal then k plus 1. So for this number 2, we need this math, and for number 3, we need this math. We can see this is larger than this and larger than this. So this is a basic review about comparison and measure beside man. And now we are considering the compressive sampling as distributed source coding. And there are many different scenarios. And first, I'm consider something about the compression. So if we have some signal, for example, we have x1 is a vector and x2 is a vector. If they are joint Gaussian, then we can see the distribution of x1 and x2 is something like this. This is ellipsoid. In 3D is an ellipsoid, and we can allocate the beat for the compression of x1 and x2 according to the variance along the axis of the correlation. And this is the basic scenario for compression, the joint Gaussian source of a 2-dimension. If you have a 3-dimension, then this is a ellipsoid. And this is 3. And you can have more dimension. And if we consider the sparse signal, the distribution of this sparse signal is not satisfy this distribution. So if we consider U is Fn, and the sparsity of U is K, and we suppose UK is the non-zero element in U, and Sj is the position of those non-zero elements. So if we know UK and SG, then we can recover the signal U. Right? So this means the position of non-zero element, and this is the value of the non-zero element. And so they are not drawing Gaussian, so we can just quantize those information and send it out to the coder. We do not need allocate the bit for each variable according to the drawing Gaussian distribution. And so in this case, we have many different scenarios to comprise a sparse signal. And the simplest way to do it is here's a table. Before we talk about the scenarios to comprise the sparse signal, we talk something about the model. And the noise model. Suppose UK is Gaussian, according to a Gaussian distribution with 0 mean and variance 1. And then we can see the expectation of U here K is the number of non-zero elements. And since B is we have X equal to B and Q. Here B is the orthogonal matrix. So we have it's also equal to K. And so for the measurement matrix here, phi, we try to make sure the variance of y is the unit. So we like the entrance of y of phi according to the distribution and working here. Yeah. So in this case, it makes y. This guarantee y, the variance of y is unit is equal to 1. Because the variance of k is alpha x is here. And then we suppose here y is a continuous variable, and if we want to transmit y through a channel, we must quantize it to a discrete variable. So we will introduce the quantization error, and we suppose y hat is the quantized value of y, and we introduce a new parameter rho here, and this is a continuous variable yi, and this is quantized value, and pass a noisy vi. Here we suppose rho is equal to 1 minus beta. And beta is the relative quantization error, which equals to 1 minus beta can be felt as the power of the original signal after quantization here, and plus the quantization error here. So we define the context y equal to rho times original yi plus the quantization error vi. And here I is the s elements in the vector y. The mass of y is the m. And then we can find vi equal to yi minus rho I. So this is the variance of quantization error according to this formula. And if we optimize the compiler, we can make the quantization error is independent of the original signal yi. There are some methods to get rid of this item. So the quantization error is independent of original signal. And here we define the quantization error here. And the quantize the variable of the signal yi. And I will talk something about the beta here. And the beta here is we can see here. This is a context y, this is the original impedance y, this is a quantization error of y and y hat, and it is a square, and that expansion, this is the variance, and this is variance of our original signal. And let's consider a quantization here. So suppose we have a signal. The signal, the maximum value of the signal is from minus from 0 to capital C. This is a signal, and this is the minimum value, and this is maximum value of the signal. And then we want to contact this this signal with an interval. We define it as here, and so suppose this is a yi height. So if y fall into this I will contact the either yi height. And then the expected error of this context process is equal to
Yeah. It holds really the two-tone getting if we have many different inputs, the method you choose for one side. That's it. So the total number of input is the C over it's the total number of input. So the compensation error in this case is this is the compensation error. And we suppose the distribution of y is uniform. So this means each y can be uniformly distributed in some intervals. So the probability of a variable fall into this interval is 1/30. And then we take an integral from minus delta over 2 to delta over 2. We can see we suppose that's very nice. So here is the this is Quantization equal to this integral, and then we can integral this then we can add so this one told us if we use a uniform quantization algorithm, the distortion is bounded is equal to only related to the compensation interval right here, and if we suppose the compensation rate equal to this value, and this is the number of interval. Then take out 2 is the number of beats to represent this compensation, and if R here we get the rate distortion relationship here. According to this formula, we got this, and the plus third here we got
This is a rate distortion relationship. So we given a rate, we can get the distortion.
Excuse me, is there any relation between d beta and sigma v power 2? D beta and sigma v power 2?
No.
D beta and sigma v.
No, it doesn't depend on the sigma beta. Actually, this is sigma square. This is so it only depends on the rate and the original signal. So you can consider this is a constant. So any distortion can be represent something like this. This is a constant.
So if a source is Gaussian, then we can get these equal to. Suppose the variance of the original signal is equal to 1. Otherwise, we should add a constant here.
Is it sigma signal or sigma noise?
The signal.